Hello, everyone. Welcome to this EC Distinguished Speaker Series. And today we have a speaker, Professor Zhaowei Liu, who is a professor in the Department of Electrical and Computer Engineering, Material Science and Engineering program, and also at the Center for Memory Recording Research at University of California, San Diego. Professor Zhaowei Liu got his bachelor's and master's from Nanjing University in China. And then later he did his PhD in mechanical and aerospace engineering from UCLA in 2006, and then subsequently was a postdoctoral researcher in NSF Nanoscale Science and Engineering Center and Mechanical Engineering at UC Berkeley, where he was working with Professor Shang Zhang, then who was at UC Berkeley. And Professor Zhaowei Liu's postdoctoral work at Berkeley has been so famous, especially with the first demonstration of hyperlens, that today it is cited more than 2,000 times, and also has been selected as top 100 science stories of 2007 by Discovery Magazine and top 10 scientific discoveries of 2008 by Time Magazine. And today he is working on many aspects of nanophotonics, metamaterials, nonlinear optics, biophotonics, sensing and imaging, etc. Dr. Liu has also been a recipient of 2010 Society of Manufacturing Engineers Outstanding Young Manufacturing Engineer Award, and then UCSD Hellman Faculty Fellowship Award, DARPA Young Faculty Award, ONR Young Investigator Award, and recently he has also been he was invited as a participant for the Frontiers of Science 2010 by National Academy of Science and Frontiers of Engineering 2014 by National Academy of Engineering. Recently he has been a fellow of OSA as well. So it's my pleasure to have Professor Zhaowei Liu here as our distinguished speaker. He will be talking about the plasmonics at sub-10 nanometer scale. Now the floor is open to Professor Liu.
Thank you, Guru. Thank you very much for the invitation and also the very nice introduction. First of all, I hope everybody is being healthy and doing well in this very special time. Today is my pleasure to give this lecture, the talk on this our recent work on plasmonics at sub-10 nanometer scale. Okay, so I want to start with a acknowledgement and to acknowledge my group members and PhD postdoc, and also a lot of collaborators listed here. Most of them are local collaborators, and also the founding resources mainly from DARPA and the Gordon and the Betty Moore Foundation. So here is the list about some of our current research interests. And as you can tell, I have a list, and I'm working on, let me just use my pointer, the high-speed super resolution imaging and super contrast imaging. And the super contrast mainly means the chemical contrast, and also the contrast from refractive indices, and biophotonics, and the optical sensing instrumentation, and plasmonic metamaterials, and extreme nonlinearities, and the integrated nonlinear optics. So these two topics, they're pretty much the same thing by using each new nonlinear material to build up some nonlinear devices and system on chip. So the next topic, we're dealing with ultra-compact high-speed light sources and detectors. And we've also been working on the plasmonic enhanced LEDs, and it's mainly for the communication and the display application. So the ultra-fast optoelectronics and nano manufacturing. So today I'm gonna mainly talk about three topics, to pick up three of them and put together. As you can tell, the high-speed super resolution imaging and extreme nonlinearity and ultra-compact high-speed light sources, it's kind of hard to find the common, things from this three topic. But this is indeed one thing they are common we have to deal with plasmonic at sub-10 nanometer scale. Okay, so then that will be almost like a three, very different topics. So so I'm gonna go through one by one. So I'm gonna start with the first topic is about super resolution, microscopy. So the whole idea basically try to build a better microscope, right? So and if you look at the history of the microscope, apparently is this is a very well established field, and then for many years, and people have a different kind of a microscope, and then now this year 2020, right? So we already have so many options from the microscopy market. So then if you treat yourself, as a user's microscope, and then you need to know what type of things and what else you want to have, okay? And here is I think is a preliminary the user's wish list. And when you look at the microscope, and you apparently want to deal with very high resolution, right? And you also care about imaging speed probably. And then if you want to deal with the light, and one of the biggest advantages to use the light microscope is because light is non-invasive. So and the photo damage apparently is also important, so that you can use the light to study life cell dynamic, for example, right? You cannot use like those kind of X-ray or electron beam, although they have a much better resolution, right? And you may also want to have the 3D, and then large field of view, and then maybe also super contrast. And we'll deal with the life cell imaging. The contrast is a big deal because all the cells are pretty much transparent. And if you only look at certain proteins, a certain target, the chemicals, and then how can you separate those your target from the background, or pretty much transparent, right? The contrast is also a big deal. And as you can see here, I listed few, the major progress in the field, and then resolution, and we already have the nanoscale resolution, and that's Nobel Prize 2014, STAD and POM. These two technology can give the super resolution, based on fluorescence, right? So, however, this super resolution doesn't really coupled with any other properties, okay? And then they're not high speed, okay? They just mainly try to solve this resolution issue. If you want to have the ideal, the microscope, you probably want to have all of this, okay? All of the best properties combined together. But of course, there's no such kind of so-called like a perfect, the tool, exists. So then the best things we can do now is try to combine the multiple property, well, as many as possible, like probably 2 of them combined, maybe 3 of them combined, and to see how can we, achieve that. So this speed, and well, I listed 2 Nobel Prize here, and then they mainly provided you the opportunity to use the ultrafast pulse laser, and that to control the exposure time. Okay, is control the exposure time. For example, it's 1 pulse and you capture 1 image, right? It doesn't really directly correlate with the microscopy imaging, and now this type of technology is being combined with super resolution at this moment. Okay, so then, so you have so many of those kind of options. The question is, how can you combine multiple properties into one, a system, and then try to show you have the best, one of the best combination. It's also possible to be achieved, as current state. Okay, so resolution apparently is one of the biggest things. I try to use this one slide to tell you, how much we have achieved simply from the resolution point of view. Okay, so optical microscopy, and here this vertical line representing diffraction limit. Right? So because the STAD and POM, they already extended this kind of diffraction limit to really to sub-10 nanometer level. Okay, so it's pretty much 10 nanometer level is almost like routinely achieved by using STAD and POM. Okay, so if you want to go to even further, for example, you want to deal with the three-dimensional plot of the protein at the atomic level. Okay, so then that's the cryo-EM can do that. Actually, long before that, the crystallography and then is already established, to measure the three-dimensional configuration of the protein structure. Okay, so by the combination of all of this type of thing, and they can tell. And if you want to deal with the cell structure, subcellular structure, protein, all of the lipid, all the high resolution type of thing, you can always find the corresponding tool to get it done. Okay, and from atomic level all the way to very large scale, there's no problem. Different kind of technology can cover that. Well, but you can quickly realize there's one main thing that's missing. So when you deal with this this imaging, you do care about resolution, but you do also care as many other properties. As I mentioned in the past, when you use the optical microscope, because it's non-invasive, you want to use it to study, maybe live cell. So, okay, the resolution-wise, we covered everything, but how about the time? So, in fact, all of this kind of technology, STAT and the cryo-EM, crystallography, and then all this type of thing is very time-consuming, especially this two is very time-consuming. Well, this is one a little faster, but still not fast enough to get like a real-time dynamics. Okay, in other words, we're using this kind of technology, but now of them you can deal with a real, like a live cell, real-time superresolution. Okay, and I want to make this kind of argument. I feel when you deal with the live cell imaging, and the speed is super important. It's just like when you consider this our daily life experience when you want to deal with the, for example, GPS, right? And when you have GPS in your phone or in your car, when you travel outside, so what do you really need? You want to have the real time traffic information, right? That's just like the subcellular environment, and then you want to also have this kind of traffic information in real time. Okay. Resolution-wise, you actually don't have to deal with super high resolution. So I feel there's no need to just try to use optical microscopy technology to push it to the atomic level, okay? Because at the atomic level, if you look at this protein, they are not really very quickly to dissolve and into like atomic level component, and then gonna assemble it into the protein in real time. They're not doing that. It's just like our GPS, we don't use the GPS try to plot out the internal structure of your car, right? You just need to know, the traffic, the car, where the car is, and the dynamic for that, probably representing more, useful information. So, then I think one of the major missing things in this field is how can you get resolution, maybe like a sub, maybe from 10 nanometer to 100 nanometer level, right? A resolution, but you want to have the high speed. Okay, so the high speed is very important, partially because all the live cell they're really dynamic, right? And if you think about 50 nanometer small particles inside a live cell, and they're doing this kind of Brownian motion all the time. They're not really static. If you tell people I get super resolution imaging of a target 50 nanometer, okay, and then if it takes you like 2 minutes to get the image, so that simply means you have to kill the cell and freeze it, right? And then you do your image, okay? So then all of the super resolution optical microscopy technology pretty much is like that at this moment, okay? And then there's just means you're getting a snapshot, of the whole, dynamics, which is quite limited. So I want to give you a very brief, comparison of the currently existing technology, and I will focus on the three things. One thing is resolution, the second thing is speed, and the third thing is optical power density. So this is related with optical, the damage, right? So resolution-wise, STAT and Palm Storm, 20 nanometer was being, people choose this for a while. Now sub-10 nanometer is durable, okay, sub-10 nanometer. And then this is structural illumination. We're gonna talk more detail later time on this topic. The structural illumination can get like 90 nanometers. It's not super high resolution, okay? But the good news for the SEAM is the speed-wise is very good. You can deal with like a video speed, okay? And then there's two technology, as you can tell, the speed-wise is pretty bad. Either it's 30 second or 10 second or minutes, doesn't really matter. So then this just simply means you have to kill your cell and freeze it. So then this is simply is too slow. And the optical power density, and then you want to make sure, this kind of power density, won't kill your cell, right? So then the smaller the power density needed is better. And instead, it have some kind of, problem with that. But of course, I would say all of the technology, they are keep improving their performance, and then this number you will getting better and better. But at least at this moment, so the no technology can deal with a very high resolution and very high speed and a very low power density at the same time. Okay, that basically is our target. We try to achieve maybe 10 to 30 nanometer resolution. Well, ideally, you bring this down to 10 nanometer. Okay, I will tell you later time how can we bring this whole thing beyond the 10 nanometer level. And then you want to have the 1 millisecond, exposure time, or the frame, image, the speed is like 1 millisecond, and also with low phototoxicity. Okay, so the few technology I'm going to talk about or develop from our group is this LP theme, the localized plasmonic assisted theme, and also this metamaterial assisted illumination nanoscopy, and we call this main. So then these two technology for LP theme, we can achieve like a rough at this moment 50 nanometer spatial resolution and almost like a video speed, and then optical power density apparently is very low. So the main, and we have achieved roughly it's about 30 nanometer resolution at this moment, but we think this technology eventually can bring us, go beyond maybe 10 nanometer. And then speed-wise, and then this method probably can bring us go beyond 1,000 frames per second with very high speed. Okay, and this speed apparently faster is even better because smaller particles are moving extremely fast. Okay, so apparently the things we want to do directly apply this kind of technology for biomedical applications, and so the biomedical biocompatibility is always a consideration. Okay, and then so at this moment we focus on fluorescence imaging, but eventually we're gonna maybe to deal with non-fluorescence imaging combining with super contrast method as well. So what is our approach? Actually, our approach starts from the structural illumination. Structural illumination, and if you look at this is the object, right? So if we have illuminations like this kind of fringes patterns, if you overlay these two things together, and you end up with this so-called Moore fringe, and then by knowing illumination pattern, you actually can retrieve the object information by mirroring the Moore fringe. So if you look at the whole things from the first space, and then we collect these diffraction limited key vector within the cutoff, right? And then this is circle. So if your illumination is fringes, you do first transform, you have 0 order plus 1 minus 1 order. If you can deliver the illumination through far field optics, and then this key vector is right on the edge of the cutoff of your optics, right? So then, and then you have the 3 dots in convolution with the the whole circle here, and then you end up with this 3 disk. Okay, and that tells you by illumination you actually can extend the observable key vector into a much bigger area. So it just because the key vector of this illumination is on the edge of the cutoff, so this method can only improve the resolution by a factor of 2. Okay, and in practice, how do you do that? And you basically provide a structured illumination like fringes like that, right? You capture low resolution images, and you're gonna translate the pattern, okay, and several times. You measure several different kind of low resolution images. You rotate the orientation of the fringe, and you translate several times. So you basically collect a multiple low resolution images, and then you go through a reconstruction algorithm. Now you can get a high resolution. As I said, this high resolution means 2-time resolution improvement. But this 2-time resolution improvement and is already very useful and very important. And then this is the state of the art of the scene. And then this is the Palm guy, the Eric Beltic now is also working in this field. You can see here traditional diffraction limited images and the same, and get although it's only about a 2-time resolution improvement, but you already can see a lot more details. Okay, and then as I said, good news, you can deal with a movie and 50 frame per second. And for example, here, as you can see, you can get a movie for kind of a biological system, and my atomic spindle, you can see the higher resolution movie can be obtained. Okay, so that's basically the benefit. But the problem is, this traditional theme is only give you about a 2-time resolution improvement, which is limits resolution to about a 90 nanometer. So then the question here, can you still use the same idea? You have this kind of high speed ability, but improve the resolution, go beyond the 2-time resolution improvement. So that's the reason we bring the idea of the Plasmonic, right? So then I assume everybody of you knows the Plasmonics, and then the benefit is the Plasmonics have the key vectors much higher and then free space light. Okay, so if we combine the Plasmonics idea into the structural illumination, and then it's very straightforward, and basically the key vector of third plasmon is higher than the key vector of light. Now you can bring the circle into the much higher key vector, so you can cover much bigger key vector information that you can get better resolution, right? So that's what our first idea, we call it Plasmonic structural illumination, called PC. So then so it's a pretty straightforward idea, and we just utilize this kind of a structured film, and then you have the light coming, hit on the film, and then the light will be converted to third plasma. And then when the plasma overlap, you will have interference pattern, right? And then you change this incident angle theta here, and then you can see the pattern this also translate, right? So you can translate along the horizontal direction. Okay, so by using this kind of method, you can deal with Plasmonic structural illumination. And then this first experiment we did quite a while ago, we had this 3D, this kind of mesh structures, and then you can change the incident angle, and then, or you can tune the fringes both along the x direction and also along y direction. Okay, by collecting multiple images, low resolution, you can end up go through a reconstruction algorithm. We also use this kind of blind sim algorithm. This is like a minimization method, and then detailed written in these papers. And then we make assumption, this is all the illumination pattern basically added up equal to a constant. Okay, you have multiple illumination pattern added up equal to uniform constant. So and then we can reconstruct not only the object but also the illumination pattern at the same time. So this is the epifluorescence diffraction limited type of thing. After reconstruction, the PCM, we get the better resolution, right? So this first space, as you can tell here, and the resolution improvement is only about 2.7 times. It's not super, but this was one of the first experimental demonstrations that we can use plasmonic interference to combine with structural illumination to get the improvement factor go beyond 2. Okay, so and you can deal with fairly large field of view. It just depends how big the size can be. It's only limited by your CCD camera. Okay. Okay. So then the question: how can you further improve the resolution? So the photonics and the far field optics can extend it to about a 2-time enhancement, right? How about if we only use the plasmonic to cover the bigger area? Okay, so then now from here you can see here this 1-time, 2-time, 3-time, 4-time, this 4-time resolution improvement, which is no problem. We can do it. Okay, and we had papers talk about this, but this is only 4-time resolution improvement. Okay, so then the question is, how do you get this kind of very high key vector of plasmonic? If you want to deal with interference and the high key vectors plasmonic wave, the propagation length is also very, very short, and you want to rely on this interference, and it may be a problematic. And later time we think, okay, let's don't use the interference. Let's use the localized plasma resonance. So then we can simply introduce the particle array, and then you can tune the period, and this period give you the reciprocal vector, and this vector is what can be very, very high, right? This is independent to this propagating surface plasma dispersion curve. Okay, so the idea actually is quite straightforward. Now you just need some kind of a particle array, very large particle array. And as you can see here, this particle size 60 nanometer, and the pitch, whatever you like, and you can tune it, right? And just do e-beam lithography. So when you look at the side, this side of you, this particle, silver particle, and then when you have the light hit on this particle, and you're gonna excite localized plasma resonance, right? So when you have the incident light, incident angle like this, you have the dipole resonance. But when you change your incident angle, you also have the dipole resonance. But the dipole, you can see here, the field loop is kind of like rotating, right? It's always perpendicular to the incident, this plane wave. Okay, so if you put your object here, right, at this dotted plane, this is my object plane. As you can see, the pattern is changing with your incident angle changing, right? Illumination pattern is changing. So then, as you can tell, if you change the incident angle, the structure illumination pattern is changing. So we just need this kind of a high resolution pattern, and they are like effectively scanning, then the object plane, and then everything will be good. Okay, so then with that kind of method, and we can achieve even better resolution. Now this is, you can see here, diffraction limited and after our reconstruction, and then using this method, and we get roughly about 3x resolution improvement. Okay, and the 3x come from basically the plasmonic that's kind of cut off, right, overlapped with the diffraction limit. So then that is about 3 times. Okay, and we apply the type of thing for biomedical imaging, and this is just one example. And I realized basically, if you want to make this imaging technology more meaningful, and you probably have to work together with biologists. And this is one of the first experiments we've done with local neuron biologists. And then we study this the neuron imagings, and then this is without our method, this is epifluorescence imaging, and with our method, you can clearly see much better resolution. Okay, and you can see this kind of small features like a 74 nanometer clearly resolved. Okay, and then we are collaborating with them right now, and try to deal with some kind of dynamics imaging, and to see whether our tool can help them to solve their problem in their own field. So we also tried this kind of dynamics and using a slightly different objective. Well, this is like a microtubules, and it's not moving very, very fast. Some location you can see is vibrating. Okay, and we can capture that movement. Okay, and this example is 4 hertz, but we can do maybe like 20 hertz level, and resolution wise, and then we get it's about this is on 43 nanometer. This is about 54 nanometer. This is about like 50 nanometer level by using the conventional objective. Okay, so far as a localized LPC, and this pretty much the best things we can do is about 50 nanometer. Okay, and it's a few times better than diffraction limit. Okay, okay. So then and then we have this kind of setup in the lab, and this is almost like a click a button type of thing. You put your samples on, and then you click a button, everything will be automatically done. You get 50 nanometer almost movie speed. Okay, but apparently 50 nanometer still not good enough. Okay, let's see how can we further to improve resolution and maybe also the speed. Okay, so then so we now working on this new technology. We call this main metamaterial-based illumination nanoscopy. So we basically have to utilize a planar the metamaterial, and how to be a planar, and we also combine it with compressive sensing to improve the speed. So then we have to do very high speed operation. Okay, so then this chart tells you that in the center the wide field is lambda over 2 resolution. The same, you probably branch to 2 times resolution improvement is 4 a lambda over 4, and the dash the circle probably LPC, we can get maybe 3 to 5 times resolution improvement. But we really want to bring this to much bigger to see how far we can go. Maybe like a lambda over 20, maybe lambda over 50, right? So then we really want to bring the whole thing down to sub-10 nanometer level. So as you can see here, we may also have to deal with the different colors of the illumination. So how the whole thing works? Basically, and the first we have to deal with this metamaterial, okay, planar metamaterial, and we want this kind of material to have to support very high key vector information. So, and this is actually being people have been talking about this for a long time, and this is very old paper and talking about hyperbolic metamaterial, and then so then the light will propagate in this hyperbolic metamaterial towards specific direction. And if you look at the transfer function, and then the key vector is actually can go very, very big, right? You can go to maybe like a K0, maybe 40, 50 level, right? So then you can theoretically achieve almost like 5 nanometer resolution. But of course, you have to make sure your metamaterial quality is enough. Okay, it's good enough. Whether you can make this type of thing apparently is also a big deal. So how can we utilize this type of thing to make a microscopy method? Okay, let's take a look. So let's assume you have this multi-layer hyperbolic metamaterial. Right now, I will have a maybe a mask, have very small slit, right? And then when the light hit on that, so it's because it's hyperbolic, and then the light only propagated along very specific direction, actually like that. And if you just zooming that area on the top surface, it's like that. Okay, and this basically have a local illumination spot. It's very well confined. Okay, this can be 10 nanometer level, 20 nanometer level, and very high confinement. Okay, so the good thing is, this hyperbolic metamaterial is very, very dispersive. So when you have the different color of the light come out from the slit, they're gonna spread out at different location. Okay, so then you can take a look. The different color of the light gonna spread out at very different location of this. So we try to use a different color, and to spread out on different location. So that we can use this kind of methods to scan the surface effectively. So we're gonna use a different color to scan different location. Okay, so so we did some kind of preliminary test, and then by I won't go through the fabrication in very detail, but although we spent years on this kind of fabrication details, it's very time consuming. So then we just grow the multi-layer, and then on the one side representing the object, the other side representing the illumination structure, and then the source, and this is the object. The light comes from the top, and the different colors spread off different location, right? So you can see here, and then if you want to reconstruct this object, you actually only need to collect the spectra in the far field, okay? And the different color gonna hit on the different object and give you some kind of spectral information, right? So that we have multi-layer, and then this is the source, okay, and then so this multi-layer, we spent so many years to try to improve the multi-layer property, and we're gonna come back to this later time. But when you have this kind of multi-layer, it can support very high key vector propagation, and then you have the object right there, and then in the far field, this kind of curve actually is the spectrum we measure in the far field. Okay, you measure the spectrum, you can directly map this spectrum into the object. Okay, and then this just tells you that we can use the spectral information to represent the location of the object for imaging. But this is as you can see here, this is only one-dimensional, right? It's not two-dimensional. So how can you convert it into a two-dimensional super resolution imaging method? So then we had to do the following, and then we basically the illumination structure had to be a small hole. So the light comes from the bottom, and the light goes through the hole, and then when the light come out, and then propagate in the hyperbolic nanomaterial, and they're gonna spread out into a cone structure, and then when they achieve the top surface, a different color is gonna spread out the different radius. Okay, so then what you have to do, for example, I want to do imaging within this red area. Okay, I'm gonna put a lot of those kind of hole at the bottom surface. So this is a blue circle representing my hole. Okay, and this is one of the hole, and then the light goes through the bottom hole, and they propagate to the top surface. They will end up with this kind of rainbow on the top surface, okay, to interact with my object. So then from this hole, you end up with one rainbow on the top surface, and from the other hole, you have another rainbow, right? You have so many holes, you have so many overlaps on the top surface, right? If you look at this small area, so then what do you have? You will have, okay, the different color have a different kind of pattern, okay? So I'm gonna make one very big assumption here, because all the hole, the location of my hole, I'm gonna pre-design it. I know the location of the hole. I know the properties of my hyperbolic metamaterial, so that I know the rainbow very precisely. So in other words, I know the whole movie, this pattern, very precisely. So all of this kind of information is my prior information. The rest of the job, I'm gonna put my object within this field of view. I'm gonna only measure the far field scattered spectra. Okay, the one-dimensional data, which is spectra. But I'm gonna use this kind of the whole pattern as the prior information and do the reconstruction. Okay, and I'm gonna apply the compressive sensing method, and which is, the Valley started this kind of sensing things, here in this field, right? So then using this kind of method, and then to deal with the compressive imaging reconstruction, right? And then we measured the spectral information, and we know that here, all of this kind of a sampling matrix is the movie I just showed you, okay? And then this is some kind of preliminary reconstruction, and then we have the numerical experiment, and this is the object, and then we measure the spectra in the far field, and we have a two polarization, right? And we have two polarization. We measure this spectra, and we go through the reconstruction process, and we can reconstruct the image like this. Okay, of course, you can see here with some kind of noise, but this pixel size is about 6 nanometer. So by using some kind of practical material property and a scattering coefficient, all the optical condition, if it works very well, we probably can give the resolution like this level is sub-nanometer. But apparently, there's so many things need to be done by to go through the whole experiment. Okay, and then actually the first thing need to be done is you have to deal with good enough properties. And then within the last many years, and we keep improving the multi-layer quality, and from each layer of the silver and the glass, from the 10 nanometer level and to 5 nanometer level, and now recently we got each layer of the silver is about 1 nanometer level. Okay, so then the apparently this period is gonna give you the upper limit of the key vector that can be supported in this material. And of course, material loss, volumetric scattering, all of the type of things also matters. Okay, so we think in this material that we can support the wave, maybe the sub-10 nanometer is no big deal. We're using this kind of material to combine it with the first method to deal with the high-speed imaging at this moment, but we haven't done the whole thing yet. Okay, well, but this is one type of material, and we also need to deal with biomedical, the compatibility issue, right? So then, and we recently we developed another organic hyperbolic material, and the P3HT, and then we use the P3HT, and we just only deal with the concentration and spin coating that we can end up with hyperbolic property, and then compared to the silver-based hyperbolic property. Very surprisingly, the figures merit can be slightly higher, okay, higher than silver in certain conditions. And then just because this material is organic, and it's very easy to work with the biomedical samples. And then there's in fact the most of our current experiments is mainly done on this is the optical this organic hyperbolic material. And the fabrication extremely simple, just spin coating. Okay, so although we are doing this high-speed imaging at this moment, but I can tell you we stuck somewhere because we do not have a high-speed tunable laser, and then we're building up the laser. But the meanwhile, we try to use this kind of material system to see we can deal with high resolution. And one things we did is we used the speckle as the illumination, and then partially because our sample quality is not high enough, and you have volumetric scattering, and then you shine the light, to this multi-layer. You actually form this kind of speckle pattern on the top. If your material is perfectly uniform, you shouldn't have this kind of speckle. Okay, this means our material is not good enough. And on the one hand, we keep improving the material property, try to get rid of the speckle. But meanwhile, we can use the speckle to do some kind of imaging as well. Okay, so this is the laser speckle. This is like a speckle go through our hyperbolic metamaterial. You can get a much higher resolution speckle, and then when you use the speckle, illuminate it multiple times, you can also use it to form a super resolution image. So then we went through this fabrication, etc., and we have different illumination wavelengths, different angle, and you can end up with a different illumination speckle. And then this is one experiment that you can see here. And we have object, right? And you measure the image in the far field is like this. It's just almost like one dot, right? But as you can see, the different different time you end up with this, the dot is moving. After our reconstruction, we can reconstruct something like this, because our speckle is super high resolution speckle, right? So and then we have like 4 quantum dot on the surface, and then we can perfectly reconstruct that. And then the center is 80 nanometer, and you can see here the line width maybe like 20, 30 nanometer level. Okay, this is something we can do at this moment. And then we also apply this type of thing for biomedical imaging, and for the microtubules, and we can get like a 35 nanometer resolution, on the surface. Okay, so when we use plasmonic metamaterial, this one thing is always, and this is away from the surface, you get exponential decay. This is mainly for surface imaging, not for volumetric, right? But actually, the one good thing is in the actual resolution, and we can get super high resolution. So the reason is because we can utilize the so-called Poisson factor. When the light emitter, they're very close to the hyperbolic metamaterial, and their lifetime or their photobleaching speed will become highly dependent on the separation of the D here. So if we can calculate the Poisson factor, right, and dependence on the D, the Poisson factor is like this, and then close to the hyperbolic metamaterial is like this, Poisson factor dependent. But on the gloss, apparently you see no dependence. And if you, based on this Poisson factor, you can convert it to a lifetime fluorosphor or the photobleaching rate, okay, and then you can get the dependence on the D. So you can measure the photobleaching speed and you can retrieve this location, right? And based on this is the idea, and then it's very simple that you put your sample cells on this hyperbolic metamaterial, you capture a movie over the time, you see the intensity gradually reduce, and then at each of the pixel, and you can figure out this bleaching speed, and just because they're like the distance to the surface is different, so the decay speed will be also different. Okay, and then we calibrate the system by adding this spacer nanometer to 100 nanometer, right? We can measure the intensity in the far field and then photo bleaching speed, and we can retrieve its original separation to the surface. And then we can, very close to the surface, our resolution can be about 2 nanometer level. This is localization accuracy. Okay, we combine this kind of information. This is the things you can do. You have a cell, and we label the cell, the cell membrane by using fluorescence. Now this is traditional photoluminescence imaging, right? And this is one we plot out the photobleaching lifetime, and we convert the photobleaching lifetime into the cell membrane separation to the surface. Now you can see here that the very high resolution can be achieved. Okay. So now I think I spent probably too much time on this imaging part, and then I introduce you the PCM. We can get resolution about 100 nanometer, but the local plasmonic illumination we can deal with 50 nanometer. So if you want to deal with the metamaterial-based domain, we have shown about 30 nanometer resolution, but we are working on that, try to extend it to 10 nanometer or even sub-10 nanometer level, although the actual resolution is already very high already. So then the combination of domain and compressor sensing, and this part will be our major focus in the coming maybe a few years, and 10 nanometer and sub 1 millisecond at the same time. I think is possible. I just need additional time to figure this out. Okay, so I think this is pretty much the first topic I want to talk about. So I won't stop here, and if you have any question, we can have a brief discussion.
Yes, thank you. I think there is a question. I guess it's Pratiksha who has a question. Can you speak, Pratiksha?
Yes. So I wanted to ask, like, if how do the absorption and scattering properties of the object that you are trying to image affect the resolution of the system?
Oh, okay. So far, and all the imaging I showed to you, is so far is the fluorescence imaging. Okay, the fluorescence imaging, and then the scattering type of thing or absorption, they're gonna modify the illumination pattern, right, locally. Okay, so that's partially the reason we cannot assume our illumination pattern is perfectly like a sinusoidal pattern. No, you have to consider your object scattering process gonna change your illumination pattern. That's the reason we're using the blind signal reconstruction. We actually don't, because that will be modified by our object. But there's only one thing we do know is the illumination pattern, the resolution is very, very high.
Okay.
And that's enough, I think.
Okay. And I also wanted to ask, is the substrate reusable? Like, if you use it to image one object, do you have to make another substrate for other object?
So, so far, our sample, we probably can use it several times, not a lot. What we're doing now, we commonly use ARD, aluminum oxide film, to do some kind of protection that you can wash off your sample several times.
Okay,
but
thank you.
When we deal with organic hyperbolic metamaterial, it doesn't really matter. It's too simple. It's spin coating. Every time we can use a new one. It's also very cheap.
Okay, thank you.
We have one more question by Alessandro.
Yes. Hi. Thank you for the talk. And I had a question about the hyperbolic metamaterial that you showed before. So you showed that basically you have to drill these holes at the base of the setup in order to then reconstruct the image of the object. My question is, so is there like so at some point each hole that you drill will not add any more information. So is there like an optimization in this, like how many holes you drilled beforehand, where you put them?
Yeah, very, very good question. All of this type of thing, you have to deal with extensive unit design. Okay, and the hole position and how big the hole, where it is, and how many of the hole, all of the type of thing, you have to be optimized. And then because this type of thing gonna modify our sampling matrix.
Right.
We basically just feed all of this kind of design, a randomly generated pattern, into a deep learning algorithm and those type of things, and to end up with one reasonable pattern. This is also possible to be done experimentally.
Okay. Yep. Thank you very much.
Sure.
Cool. There are no more questions. I think we can.
Okay, so now I'm gonna switch gear a little bit. Quantum plasmonic with stream nonlinearity. So this is actually plasmonic metamaterial being there for a long time, right? And then so this as we know, this field we pretty much got the metal all the time. Okay, and all of this kind of application we use metal, and then the metal, and then we pretty much majority of us using this kind of juice model, and then it's just like a very convenient, very useful, and then as you can tell, from our well, I would say not only as many people in this field, and then gradually to deal with this kind of nanoscale plasmonic structures, and then So then non-local model had to be utilized when the particle getting smaller or the structure separation getting smaller, and so many works been done in this field. I think Rice and then Naomi Hellas and Peter Leonard, and there's also the pioneer in the Plasmonic field, and so many beautiful works been done, and then so that's one thing. We realize all of this. The previous work, right? People care more about the geometries, and then you have the quantum corrected model, and you have this electron tunneling, right? And you have the particle getting small enough, and you also have to do quantum plasma, the correction, all that type of thing. But we actually mainly care about the one thing, because as you can see from our last topic, we're dealing with this multi-layer, and then we shrink the size smaller and smaller, and then the size, the thickness of the metal layer, it becomes so thin, and then when this metal layer gets very thin, we apparently know the electron inside the layer get quantized, right? This is very old, the papers more than 20 years ago, and then electron quantization in the metallic well, right? So then what our interest is, how about we just think about when the light hit on this kind of a metallic layer, what will be the optical response? Okay, not well, very beginning we mainly care about this linear response. Okay, and then we basically came up with this model. It's a very simple model. I think it's nothing really special. It's just a quantum electrostatic model. We treat it as like electron in the box, right? And then so then this is metallic quantum well, and then sandwiched by oxide. So this well is very, very deep. You have many quantized state, right? So you have this. You use Schrodinger equation. You solve the equation. You get this state energy and a function, and then you also need to care about the electron distribution using the Poisson equation. You get this kind of electron density distribution, right? And this kind of modify the Schrodinger equation, and then you deal with iteration. Eventually, you get a stabilized solution, and based on that, you can use this kind of equation, basically all this Lorentzian kind of resonance type of thing, add it up, and then you can estimate the permittivity. And then you also need to consider the electron-electron interaction, which is like effective relaxation times. You can do a correction, right? You can estimate this material property. Okay, and then so we get this kind of a thin layers model, and then as you can see here, right, the thickness is about around 3 nanometer, maybe 2.5 nanometer level. Okay, so then we measure this optical property, and you can tell here, very thin layer. This is red one. This is the linear N and K. Red one is 2.5 nanometer. Retrieved NK, okay, and then this blue and red is relatively thicker metal film, and this is pretty much close to the bulky Lorentzian, the juice model. But you can tell this thin film, they are very different, okay, very different. And then our solid line, this is from our first this kind of model, electrostatic model, and it can describe this type of thing very well. Okay, so then, well, it's more exciting things from this actually. When you solve all of this kind of previous equation, you get an electronic state, in the quantum well done. You actually can also calculate its, chi2 and also chi3. So the why this is, we think this is exciting. Actually, this is, initiated from I would say, an accident. So then we got this multi-layer, this kind of very beginning, actually single layer as a metal film. And then we want to do some kind of measurement. And then our student put it under our like a femtosecond pulse laser. And then this is the infrared. And then, but when you put the samples on the stage, when the laser hit on the sample, and we see it's very bright light, actually visible light. So we get very confused. Hey, why? This sounds like it's visible. And probably we just simply burn out the sample or something. What happened? And then we realized probably there's some kind of like a nonlinear effect. Okay, and then we start to look at this nonlinear response. And then I just want to quickly, tell you that, for example, the chi3 is proportional to the n here is the density of the free electron. and this is the dipole transition element mu. Both of the two components are very, very high in metal. Metal, apparently electron density is the highest possible from all the materials, right? And then this is one, the dipole transition element is proportional to the quantum wall side, which is much bigger than the traditional nonlinear, the dipole size, which is maybe angstrom or maybe sub-angstrom scale, right? So then combine both the two things, and then we can get a very high value. Okay. Let me just a moment. I think somebody's playing piano outside. Okay, sorry. Okay, so then for this now let's take a look. What kind of Chi2 and Chi3 this material can give you. So then, and in this in gold that we get like a Chi3 is about 2 times 10 to negative 15, and this number is about 5 orders higher than the bulk of gold. Okay, just because you make it very, very thin, and then and this is among the highest possible Chi3 for all the materials, and this can be even higher than the graphene. So for Chi2 you have to break the symmetry, and breaking the symmetry in this case is we can just use the barrier on two sides. Okay, the barrier height is the change is small, but that's enough to give you like 250 picometer per voltage level. Okay, and this is good because the gold film, we don't need to have any fancy this kind of machine. It's just sputter machine. You can sputter on any substrate. This kind of oxide is working very well if you control the sputtering condition. Okay. But this is maybe very difficult to deal with atomic level control and the surface roughing and all that type of thing, right? And also the gold, you don't want to deal with very high power density, so that and then this laser gonna, if you have any defect or roughness, and they're gonna easily burn out the sample. Okay, for that reason, on later time, and we convert it to this refractory plasmonic material, which is titanium nitride, which is optical property very close to gold. And then the good news for titanium nitride is that you can grow this film almost epitaxially together with aluminum oxide. As you can see here, if you zoom in a little bit, right? This aluminum oxide here, this layer is about 5 angstrom. This quantum wall is 2 angstrom, 2 nano, and this is 1 nano, right? So you can get a very high resolution, high quality, almost atomic level. This kind of quantum wall by using this, okay? And this one thing we want to deal with this because we want to work on this kind of very high Chi2 by using a asymmetrical coupled quantum wall, and that you can deal with a double transition. There's this line of very well with fundamental frequency. You can deal with the second harmonic for generation, for example, okay? And in this experiment, you have the fundamental coming, you have reflection, transmission. You can directly see this. From both reflection beam and transmission beam, you can see the color already been changed. Okay, so and then conversion efficiency, I would say, is very high because the whole material is only maybe like a 20-30 nanometer thick. Okay, so and then we measures its corresponding Chi2. Now you can see here, and we got about 1,000, maybe 500, and then there is a peak. This peak aligns very well with our the quantum wall, our designed transition. As you can see here, we designed this red, this fundamental frequency, right, and the double transition, and then depends on the quantum wall thickness. If you want to change the quantum wall thickness, and in principle, you can tune this resonance frequency and to whatever the wavelength you want to work at. So and then again. We can also combine it with the localized plasma resonance, right? You can get a very high surface SSG efficiency. And then we actually got the total power efficiency is about 10 to negative 4 from single reflection beam. Okay, so this is already very, very high, surface, SSG, effect. So you apparently can also deal with Chi3. And the Chi3, you don't have to deal with the symmetry breaking. Just single quantum wall will be enough, right? We have the multiple layer the quantum wall. You only need to design this the thickness. You measure the Chi3 is very, very high. and then you use it, you can deal with a pulse limiter. And this is, I think it's maybe 7 to 8 pairs of this titanium nitride layers, and then seven unit of the metallic quantum well can be used as a very good pulse limiter, the reflective pulse limiter. This is so you can see here that when your incident power get high enough, and then reflected power will be saturated. I think this is probably one of the first sub 100 nanometer reflective pulse limiter, just because you have very high, nonlinear coefficient. Okay, so I want to say one thing about this. This is very interesting. This when your power getting very, very low, and this is the NK. Okay, so then actually our quantum wall is metallic. When you change the incident power and to here, and then you can see, right, this is NK. Real part, mirror part, they flip, right? So at here, there's almost no loss, but it's dielectric. So here is dielectric, here is metallic. So this is a material that we can easily tune from metallic to dielectric, and by using the power. So then we think this is the maybe it's very interesting phenomenon that we can use it to build out many other different devices. And I want to show you one example. How do we use it? And then to combine it with the metal surfaces. And this is one of the reflective metal surfaces. You have the antenna on a mirror. Okay, and this antenna apparently is a plasma resonance type of thing, and it will give out a different kind of response phase and the type of thing. So then what we're gonna do, we're gonna replace the whole thing by this multi-layer. And then you can treat this as a hyperbolic metamaterial. And so then you also have the plasma resonance, but the additional things here, because this metal film is so thin, it's also give you extremely high nonlinear coefficient. Okay, this is just like the traditional metal surfaces with very high intrinsic nonlinearity from this metallic layers. Okay, and then we can design this type of thing and to have, for example, and when your power is very, very low and heat on the metal surface is almost like a reflection mirror, and when your power is high, and then this will become like a diffraction gradient. Okay, and this is the purely like Kerr effect based tunable like a metal surface. And then we get some kind of experiment done already. This is a very recent result. And you have the metal surfaces, and then you can see here, this is a metallic particle on the back mirror is replaced by hyperbolic metamaterial. Okay, and then when you have the light coming from the top, and when the power is very, very low, you see this reflection is very efficiency very high. When you improve the power, now gradually, you see, and you see the zero order becomes stronger and stronger and stronger, and this is high order almost disappear, right? And the purely is a non-linear response of this Kerr, metal surface. And then you can plot out the efficiency for high order for first order diffraction, and low power, the high order is very, very efficient, and you improve the power, and the high order is almost disappear. Okay, and you can also use the type of thing to make a hologram, and then this experimental data, and then we have the low power intensity, and then you see this hologram. When you increase the power intensity, and then the hologram gradually disappears, and then the whole thing is almost like diffraction, like a reflection mirror. Okay, so I think here is the summary, and for the giant nonlinear coefficient. We think the ultra thin metal film and provides a very interesting opportunity to get a very big Chi2 and Chi3, and then so I want to emphasize here, this is about n+1 orders enhancement for nth order nonlinearity in this metallic quantum well. So if you get like a second order nonlinearity, you probably can get 2 + 1 3 order improvement. Okay, if you deal with third order, you may get 4 order improvement. Okay, so that's roughly the estimations about that. So far, we get the value I put it here, and then we're thinking about to use this kind of Chi2, Chi3, the high, Chi2, Chi3 material, and then we put it on the chip, and to combine it with some kind of non-linear optical component to deal with either, for example, like a supercontinuum generation, and then maybe 4-wave mixing and that type of thing. And also you can think about this as the tunable plasmonics and tunable metamaterials. Everything is controllable by excitation, power. Okay. So I think I pretty much done with this second topic. If you guys have any question.
I don't see any questions yet from the attendees. I have one actually. This is related to generally how we know about what Chi3 is with metals. So they have, of course, very high value of Chi3, but also very high imaginary part of Chi3. And so metals, of course, have a free electron concentration that is large, but also have absorption, which is the reason why they're not used in traditional nonlinear optical applications. So how about quantum belts?
Okay, this is a very good question. Okay, so people from our common sense and see the metal is highly lossy, right? But this is the loss part is mainly from the linear portion. The non-linear loss actually gonna be very, very high, could be very, very high for any material. And in fact, the emitter part for the Chi2, emitter part of Chi3, and this, it can be tuned, can be designed, can be positive, can be negative in this metallic quantum world. That is something quite surprising. And as you can tell from this example, right? From this example, if you design it well at this power intensity here, right? There's no loss at all. There's almost no loss. Okay? So this portion is the non-linear part, and the linear part somehow they canceled out. Okay, so there's a lot of optimization process can be done, in that direction. Yeah.
Cool. Yeah, but this is just going back to calculations and can be designed in such a way. For an example, there is an application which demands so and so performance. Then this can be designed exactly for that particular application, right?
Yes.
Okay. Cool.
Just Guru, I don't know. This is already a 2:10. Do I have time to talk more, or I can stop here if you want?
Yeah, I think since usually most of the seminars are around 1 hour, but I haven't really set any time restriction on this. It's really very interesting. I guess we still have attendees who are interested, and I would not mind listening for maybe another 10 more minutes.
Okay, so then I will try to finish up, the last topic maybe in 10 minutes. And then, so then this is like a completely independent topic. It's like the light generation from the metal insulator, metal tunneling junction. So the whole idea is that we try to develop a new light source. Okay, and this new light sources have to be very big bandwidth, and for communication purposes as big as possible, right? Hopefully maybe terahertz or even faster. And the footprint has to be very, very small. It's sub-wavelength scale. And then we hope this light source can be tunable. Okay, and of course, efficiency always matters. Okay, and we'll see if there's any possibility that we can combine all of this kind of nice properties into one material system and put it in the middle. And it turns out it's very, very difficult. Okay, so and then our approach is using electron tunneling to generate light. And this is a very old topic. I mean, you can see here, Lamp Microscopy published paper 1976. Okay, it's a long time ago. And the electron, it tunnel. This is actually this metal, insulator metal junction, and the electron tunnel through the barrier. And then because this is on both sides, you have metal, right? The metal can support surface plasma mode. And then when the electron goes through this barrier, experiencing some inelastic scattering, and then we'll give portion of the energy to the surface plasma, and then surface plasma will be generated, right? And then if surface plasma hit on some kind of roughened surface or something, and the light come out. So then they basically demonstrate this light generation from this schemes long time ago, but the efficiency was very bad. It's only 10 to minus 5. It's very bad. Okay, so the good news for this, why the recently people came back to this topic, because the speed is extremely fast. Because tunneling takes almost no time. Okay, extremely fast generation speed, and not like an electron hole recombination, and that's a lifetime is maybe like maybe 10 nanoseconds. It's too slow, right? So then this tunneling process is extremely fast, the main problem is very, very low conversion efficiency. Basically 10 to negative 5 is make it almost useless, okay? And then the main purpose is how can we, improve the efficiency into something that's, comparable with the LED or the other light generation methods. And then this light generation scheme might be useful. Let's take a look why the efficiency is so low. And because the internal quantum efficiency, that is all the electrons, part of them have inelastic tunneling, part of them have elastic tunneling. So this ratio of inelastic tunneling, the portion is very small, and the maximum is 10%. And then the maximum 10% is because we can design some kind of plasmonic, mode or something to enhance the process. After the enhancement, you probably can end up with 10%. Without enhancement, probably much worse. Okay. And then out of coupling, and then we put down here maybe possibly 10%. Okay, if we do the optical antenna design, the optical antenna design could be much better than 10%, but because we have to combine with the field enhancement together. So then these two factors, they are correlated to each other. Very likely after optimization, you have 10%, 10% totally. You may end up with the 1% level. But all of the previous experiment by using the random surface roughness, their efficiency is very bad because internal quantum efficiency 10 to minus 3, coupling 10 to negative 2. You put together it's 10 to negative 5, right? So then we think by best optimization, we probably can bring it to like a 1% level. Okay, so that is something we did in the past, but other people also use this idea using the boron nitride or something, right? And then sandwiched by the metal film, and then you can have a metallic structure by adding the voltage and the light come out, and then you see depends on the structure size, you have a different kind of emission spectrum, right? But efficiency-wise, it's very, very low. Okay. And this the same thing, the optical antenna. This is a very nice antenna, right? And then you have this tunneling across this area, and different antenna will have a different kind of emission spectrum. But again, the efficiency you see 10 to negative 4, right? And this is another one is on chip. So they retrieve the internal quantum efficiency 10 to 14%, which is very high. But there's no light emission from this, and they basically have. This is plasma source, this is plasma detector, and then plasma can coupled through this waveguide, and then they directly mirror everything on the chip, right? But there's no light emission in the far field. Okay, but this is at least proved that internal quantum efficiency is about 14%, and if you design everything very well, okay. But this plasmonic mode, because the mode is very, very high K vector, it's very hard to be coupled to the far field. Okay, so our approach is very simple. We just basically try to use COM particle and to deal with a single crystal from a chemical synthesis and bring these two particles together, use self-assembly. We can control the separation D is very, very small. And then later time, we add electrode like this. So everything single crystal. And then this can be a very good antenna. And then this junction can be very well controlled. And then the particle single crystal and the material loss is very small. All of this type of thing. Try to push everything to the limit. And then this, we have a local collaborator and the Andrea Toss group, and they can grow this particle. They can, assemble this into this face-to-face or edge-to-edge, all of the type of thing, right? And then eventually we can end up with this kind of structure, and then we get a junction here, 1.5 nanometer and a single crystal, and then we put together and like this, and we add electrode, and by adding the voltage, we mirror the IV curve. It has a very classical, this kind of N-shaped, this kind of IV curve. And this just means the DC signal can be converted to radiation and at this location, okay? And then you mirror far field emission spectra, right? And then when you change the particle size, you see the particle emission spectra also shifted, right? So the efficiency for this one is 10 to negative 3. It's not super high, partially because this particle resonance is not designed very well because localized density state and emission peak, they are not very well aligned. If we want to align these two, and then you have to make this particle in the center, okay? You change the height of this, and then you see this two peak can be aligned very well. So then you change the height, you see the quantum efficiency will change from maybe 0.2% and gradually to about a 1% level, okay? And if you want to deal with even longer wavelengths, and then you put to like a 1.6 8 micrometer, and then you get like a 2% level. Okay, so that basically this is very quick like a summary here. And then we use the MAPM junction, and then with a single crystal, we build up the light generation, devices, and we achieve about 2% quantum efficiency. But the one thing that's really good is here is that we use one mature system, just metallic, that in principle we can generate light from visible all the way to 2 micron, right? So if you want to deal with even longer, 3 micron, this is also durable. So there should no things to prevent you. So this one mature system, you can generate very, very broad band light emission. So the 2% may not be high enough, but then the main question is it possible to deal with much higher efficiency? Is it possible to use it to build a laser, or maybe also can make a detector? So I'm gonna show you 2 slides that shows you, and that's efficiency-wise, we actually can beat this limit. And this is a very recent result. We haven't published this yet, but we're using the resonant tunneling junction. The reason here is, when the electron go through this, only the inelastic tunneling part will contribute to the light generation. But how do you block the elastic tunneling? So we just use the resonance junction. Right? You have a very thick this kind of barrier layer will be very efficiently to block the elastic tunneling. But only the inelastic tunneling, and for the tunnel here inelastically, and then go through this resonance tunneling can go through this. And then that will give very high efficiency. So then this is, you can tell, this is combined with our previous metallic quantum wall idea, right? We use this kind of metallic titanium nitride, quantum wall, and they have very thick oxide as a barrier. Okay, all the titanium nitride, this titanium nitride, right? So then, and the build up of the whole resonant tunneling junction. And then we measure the quantum efficiency. Actually, this is the experimental data we get at this mode. We get about 30% quantum efficiency. So then, because our particle, we have a plasma, we have a 2 mode. There's a 1 mode here, 1 mode here, and this 1 mode here is the efficiency could be 30%. So we think there is a way to improve the quantum efficiency, and into maybe 20-30%, and maybe in the future even higher. And the rest of the job is really try to make it more compelling. I mean, to show this more like the traditional LED devices that you have to deal with the head-to-head comparison with this other light emitters. Okay, so I think this is my last slide. Sorry about this; it's dragged so long. Right. Thank you.
Thank you very much for the talk. Again, I think attendees can let me know if they want to ask any question. In the meanwhile, I have maybe a more general question on the first part of the talk, which I wanted to ask, then somehow forgot. The question is about the natural hyperbolic materials versus the artificial ones that you showed that can improve the imaging performance. So how about using, for example, naturally occurring 2D materials? So of course, some of them might be good only in the infrared wavelengths, but suppose if there is one that is really good in visible, so how would a naturally occurring hyperbolic material compare with the layered structure?
Well, we really don't care is natural hyperbolic material or not. Okay, as long as this material can support a very high key vector.
Yeah.
So based on our experience, for naturally existing hyperbolic materials, and all of them has very high loss. And for example, here, if you look at this few materials, okay, and it's natural hyperbolic at visible frequency, because we want to deal with biomedical imaging, we have to work at visible frequency, right? So this material is too lossy. So as long as you can find the low loss hyperbolic material, and it will be fine.
Okay. So
we use this.
Okay. Yeah. The highest K vector, it's a trade-off between how much it propagates versus how high it is.
Right. So we're basically now we're looking for this material can support the wave vector around 50 K there, which is very high. Okay. 50.
Yeah. Okay. Got it. Cool. Also, maybe just a question related to the light emission part. So clearly, I think the advantage that you're getting with or increasing the quantum efficiency with light emission is mainly coming because you're reducing the K space. So you're reducing the size, so you're actually causing the K space points to be more quantized, and hence momentum matching is easier, right? So otherwise, the momentum of electrons, it's like the mismatch is too high for them to be actually injected or even the tunneling to happen. And that's what you're actually beating with quantization. Is that right? So which means you can probably do better if you shrink the quantization size or even add one more dimension of quantization.
Okay, yeah, so basically the momentum of light and momentum of electron, apparently the 3 orders different, right? So if you want to deal with very high conversion efficiency, so if you're a photon is also, the key vector is 1000 k0, then the conversion efficiency might be very high. But the problem is, how can you convert this type of thing into free space, propagating light? Then the conversion, coupling efficiency become an issue, right? So then eventually you have to, if you are looking for a far field light emission source, so then you have to optimize between these 2 processes. But if you want to deal with the plasma source, you don't want the light to come out. You just want to convert it into a on-chip plasma, and then efficiency actually could be pretty good.
Right. Okay.
Yeah.
Well, I guess I don't see any more questions from the audience. So thank you very much for accepting our invitation and presenting a wonderful talk here in our distinguished EC seminar series. And we'll continue talking later after this webinar in a separate Zoom invitation. Thank you again. We wish that you had received a small token of appreciation by now. Hopefully, you will get it soon.
No
thank
problem.
you very much. Yeah.
My pleasure. Thank you.